300 million years after the Big Bang, the universe was already producing galaxies bright enough, massive enough, and chemically evolved enough to make astronomers slow down and check the numbers again. Webb did not just find faint smudges at the edge of visibility. It found luminous systems at redshifts above 13 and 14, meaning their light began traveling toward us when the cosmos was still in its first few 100 million years, far earlier than many models expected such substantial galaxies to appear. We are going to travel through that tension layer by layer, from the first suspicious light in Webb's deepest surveys, to the mathematics of galaxy growth, to the uneasy fact that some of these young galaxies already seem to carry the weight, brightness, and stellar maturity of systems that should have needed far more time. Not a little more time, vastly more. Enough time for gravity to gather dark matter, enough time for gas to cool, enough time for stars to ignite, die, enrich their surroundings, and build structure on top of structure. But the early universe may not have waited for our timetable. It may have been building faster than our theories were prepared to allow. Take a breath. We launch into the deep. It began the way many scientific disruptions begin, quietly. Early Webb imaging programs such as GLASS and JADES started returning objects so distant that their light had been stretched deep into the infrared by cosmic expansion, exactly the regime Webb was built to explore. Hubble had looked back far, but Webb looks back with a different kind of sight. Its gold-coated mirror and infrared instruments were designed to catch ancient light that visible light telescopes miss, light stretched by the expansion of space itself, until the first galaxies no longer shine in colors your eyes could ever see. That is Webb's advantage. It does not simply see farther, it sees earlier, and early turned out to be uncomfortable. Because hierarchical structure formation, the standard picture, says the universe builds from the bottom up. Small dark matter halos first, then larger halos through mergers. Small galaxies first, then bigger ones through time, collision, accumulation, and patience. That picture has worked well for decades because it explains the large-scale cosmic web, the distribution of galaxies, and the growth of structure across billions of years. But Webb began finding candidates that seemed too bright and too abundant in the first 500 million years. Then spectroscopy strengthened the case. 2 luminous galaxies were confirmed at redshifts 14.3, 2, and 13.9, placing them around 300 million years after the Big Bang. Clear evidence that substantial galaxies were already in place startlingly early. To understand why that matters, we need to rebuild the phrase early universe from scratch. 13.8 billion years is the age of the universe. 300 million years is about 2% of that history. If the universe were compressed into a single calendar year, these galaxies would appear in the first week of January. If cosmic history were a 24-hour day, they would arrive only minutes after midnight. That is the scale of the problem. We are not talking about galaxies forming slightly ahead of schedule. We are talking about mature-looking construction, beginning when the cosmic scaffolding itself should still have been going up. And the most unsettling part is that the brightness was only the surface of the story. Because once astronomers began asking how those galaxies could shine that much that early, a deeper question opened underneath it. Brightness can mislead. Mass usually tells the truth, and mass is where the real alarm begins. Mass in astronomy is not a feeling. It is an accounting problem. You can infer it from how much light a galaxy emits, from the colors of its stars, from the shape of its spectrum, from the rate at which it is forming new stars, and, in some cases, from the motion of gas inside it. None of those methods is perfect on its own, but when several begin pointing in the same direction, scientists pay attention. That is what happened here. Some of Webb's early galaxies were not just bright because a few short-lived hot stars happened to be flaring at the right moment. Several appeared to contain far more stellar material than standard models predicted should be possible so soon after the beginning. Follow-up analyses found that some candidate systems at redshifts above 10 seem to imply stellar masses reaching hundreds of millions or even billions of solar masses, depending on the model assumptions. That is where people stopped speaking casually and started checking every premise underneath the result, because building a galaxy is slow by cosmic standards. First, you need a dark matter halo, an invisible gravitational well large enough to gather ordinary gas. Then that gas has to fall inward, shock, cool, fragment, and collapse into stars. Those stars begin to flood the young galaxy with radiation and stellar winds. The most massive among them die quickly, enriching the surrounding gas with heavier elements. New generations of stars form from that enriched material. Structure builds on structure. Time does the work. The early universe, in our standard picture, should not have had enough of it. The phrase massive galaxy is too soft for this, so let's put weight back into it. Our Milky Way contains on the order of tens of billions of solar masses in stars. A young galaxy, in Webb's first few 100 million years, does not need to rival the Milky Way to be disruptive. Even reaching 1% of that mass so early is difficult. Now imagine trying to do it while the universe is still dense, turbulent, flooded with energetic radiation, and only beginning to emerge from the cosmic dark ages. That is like finding a city skyline already rising, while the ground beneath it is still cooling. This is where infrared becomes more than a technical detail. It becomes a kind of time machine with rules. As space expands, it stretches the wavelength of light traveling through it. Ultraviolet light, emitted by the first hot stars, is pulled outward into visible wavelengths, then farther still into infrared. The farther the source, the more extreme the stretching. This is redshift, not because the object is simply red, but because its light has been shifted toward the redder, longer wavelength end of the spectrum by the expansion of the universe. Webb was engineered for precisely this task. Its instruments, including NIRCam and NIRSpec, can detect and dissect that ancient infrared light, turning faint distant smears into dated physical systems with chemical fingerprints and cosmic timestamps. That timestamp is called look-back time. When you look at a galaxy 13.4 billion light-years away, you are not seeing distance alone. You are seeing history. You are watching light that left before Earth existed, before the Sun existed, before the Milky Way had become what it is now. Webb's superpower is not merely seeing far into space. It is catching photons that began their journey when the universe itself was still becoming recognizable. And that power created a problem almost immediately, because once spectroscopic confirmation arrived, these objects were no longer just suspicious dots in an image. They became dated facts. The universe was making galaxies earlier than many simulations had prepared us for. The question then shifted from, did Webb really see them, to something more difficult? What exactly were these galaxies, and how could they have grown up so fast? The first instinct in a situation like this is restraint. Astronomers do not assume the universe is wrong. They assume their interpretation might be. Early Webb candidates were scrutinized with the same question repeating quietly through the community. Are these galaxies truly massive, or are we misreading their light? Because light can trick you. A galaxy that appears extremely bright might simply be forming stars at a frantic pace. Young stars burn hotter and bluer than older ones. If a galaxy is dominated by these massive short-lived stars, its brightness can exaggerate how much mass is actually present. In other words, a galaxy could look enormous while actually being relatively lightweight. So researchers began modeling alternative explanations. Perhaps these early galaxies were dominated by massive stars, far larger than typical stars forming today. Perhaps star formation in the early universe was unusually efficient. Perhaps dust, metallicity, or gas conditions altered the spectral signatures in ways that fooled the models estimating mass. Each of these ideas softened the tension slightly, but none erased it, because even when astronomers adjusted assumptions in the most conservative direction, the numbers still suggested that galaxies were assembling quickly, sometimes uncomfortably quickly. Not just one or two rare objects, but a population emerging in Webb's deep field surveys. And that is when the discussion turned towards something deeper than individual galaxies, structure itself, because galaxies do not grow in isolation. They grow inside dark matter halos, vast, invisible cocoons of gravitational influence that form when cold, dark matter collapses under its own gravity. In the standard cosmological model, tiny density fluctuations left over from the Big Bang slowly grow larger over time. Regions that begin slightly denser attract more matter, becoming seeds for galaxies. This process is patient. Computer simulations tracking the evolution of the universe across billions of years show the cosmic web gradually emerging. Thin filaments of matter stretching across enormous distances, knots forming where filaments intersect, and galaxies lighting up along these gravitational highways. But the simulations share an important rule. Small structures first, large structures later. The earliest galaxies should therefore be small, irregular, and faint. They should grow slowly as mergers accumulate mass across hundreds of millions of years. Webb's discoveries suggested something slightly different. Some galaxies in the first few 100 million years looked not like fragile beginnings, but like systems already well on their way toward maturity. Their stellar populations hinted at earlier bursts of star formation. Their luminosity suggested a surprising amount of material had already condensed into stars. In some cases, astronomers began describing them with a phrase that carries quiet weight: too big too soon. And when scientists say something formed too soon, what they mean is not that the universe made a mistake. They mean our model of the universe might be missing something. The next layer of the story moves outward, away from individual galaxies and into the environment they were forming inside. Because galaxies grow fastest when gravity has help, when dark matter halos collapse efficiently, when gas falls inward without disruption, and when early cosmic conditions allow matter to gather quickly rather than slowly. The early universe may have been more cooperative than we expected, or something else may have been helping gravity do its work. For decades, cosmologists have relied on a framework known as lambda cold dark matter, often shortened to lambda CDM. It is not a single equation, but a broad structure of assumptions describing how the universe behaves on the largest scales. Lambda represents dark energy, the mysterious force driving cosmic expansion. Cold dark matter refers to the invisible matter that forms the gravitational scaffolding of galaxies and clusters. Within this framework, the early universe begins almost perfectly smooth. Not entirely smooth, tiny fluctuations exist, differences in density of about 1 part in 100,000. Those minuscule irregularities were mapped in exquisite detail by observations of the cosmic microwave background, the faint afterglow of the Big Bang. Those fluctuations are the seeds from which everything grows. Gravity amplifies them slowly. Slightly denser regions pull in surrounding matter. Dark matter collapses first because it does not interact with radiation the way ordinary matter does. Baryonic matter atoms, gas, and dust falls into these dark matter wells later, eventually igniting the first stars. Over hundreds of millions of years, the earliest galaxies emerge along filaments of the cosmic web. This gradual process explains the large-scale architecture of the universe remarkably well. Simulations based on lambda CDM reproduce galaxy clusters, voids, and filaments across billions of light-years. When astronomers compare these simulations with observations of nearby galaxies, the match is striking, which is why Webb's early discoveries created tension rather than celebration alone. Because if galaxies were forming faster than predicted, it might mean something subtle but important about that early environment was different. Imagine the cosmic web as a landscape slowly rising from a calm sea. Tiny ripples grow into waves, waves into currents, currents into structures spanning millions of light years. The timing of that growth is governed by gravity and the density of matter in the universe. If galaxies appeared earlier than expected, it suggests the ripples may have grown faster, and faster growth could happen for several reasons. One possibility is that the early density fluctuations were slightly stronger than current measurements suggest. If certain regions started out denser than average, gravity could have accelerated structure formation locally. These rare peaks in density might produce galaxies sooner than expected. Another possibility lies in the nature of dark matter itself. The phrase cold dark matter assumes dark matter particles move relatively slowly compared to the speed of light. Slow particles clump easily, allowing halos to form efficiently. But if dark matter has properties slightly different from what we assume if it interacts weakly with itself, or possesses a range of particle masses, its collapse behavior in the early universe could shift in subtle ways. A third explanation involves star formation efficiency. Early galaxies may have converted gas into stars far more efficiently than modern galaxies do. If primordial gas cooled quickly and collapsed rapidly into stars, the brightness Webb sees might reflect extremely vigorous star formation rather than large, mature stellar populations. Each of these explanations adjusts the story slightly without rewriting it entirely. But there is another reason scientists are cautious, because the brightness and mass estimates of these early galaxies depend heavily on interpreting faint signals stretched across billions of years of cosmic expansion. A small shift in assumptions, dust content, stellar populations, chemical composition can dramatically change how massive a galaxy appears. In other words, Webb's discoveries sit right at the boundary where observation meets interpretation. The data are real. The galaxies are there. But exactly what those galaxies represent in terms of mass, structure, and evolutionary stage remains an open question. And that uncertainty is precisely what makes the discovery so compelling. Because if even a fraction of those early galaxies truly are as massive as they appear, the timeline of cosmic structure formation may need adjustment. Not a collapse of the standard model, but perhaps a refinement. A recognition that the early universe was capable of building things faster than we once thought. Which brings us to the deeper mystery. Not simply how galaxies formed early, but how the first generation of stars lit the universe in the first place. Long before galaxies existed, before spiral arms and clusters and glowing nebulae filled the sky, the universe passed through a quiet period that astronomers call the cosmic dark ages. It sounds dramatic, but the phrase describes something very simple. After the Big Bang, the universe expanded and cooled. Roughly 380,000 years after that beginning, electrons and protons combined to form the first neutral hydrogen atoms. When that happened, light was finally able to travel freely through space. The faint radiation from that moment is what we now detect as the cosmic microwave background, the oldest light we can see. But after that glow faded, the universe entered darkness. No stars existed yet, no galaxy, no luminous structures of any kind, just vast clouds of hydrogen and helium drifting through space under the influence of gravity. For tens of millions of years, nothing shone. Eventually, gravity began to change that. Dark matter halos formed first enormous, invisible regions where gravity was slightly stronger than average. Gas began falling into those wells, compressing slowly. As the gas collapsed, it heated up. When it became dense enough, nuclear fusion ignited. The first stars were born. These stars were unlike the ones we see today. Modern stars contain heavier elements, carbon, oxygen, iron, produced by earlier generations of stellar explosions. The first stars had none of that. They formed from almost pure hydrogen and helium, the original ingredients created in the Big Bang. Because of that chemical simplicity, the physics of their formation was different. Without heavier elements to help gas cool efficiently, enormous clouds of hydrogen collapsed into extremely massive stars. Some theoretical models suggest these population 3 stars could have reached masses hundreds of times larger than our Sun. Stars that large burn fast, very fast. They blaze through their nuclear fuel in just a few million years before exploding as supernovae, scattering the first heavy elements across the cosmos. Those explosions enrich surrounding gas, allowing later generations of stars and eventually planets to form. In other words, the first stars were the universe's chemical factories. But they also had another job. They reionized the universe. When the first stars ignited, their intense ultraviolet radiation began stripping electrons from neutral hydrogen atoms in the surrounding intergalactic medium. Over hundreds of millions of years, this process gradually transformed the universe from a cold, neutral fog into the transparent, ionized plasma we see today. Astronomers call this transformation the epoch of reionization, and Webb's early galaxies appear to exist right in the middle of it. That is part of what makes them so valuable scientifically. These galaxies are not simply distant objects. They are markers in cosmic history signposts, showing us how quickly the first structures emerged after darkness ended. But they also hint at something else. Because if galaxies were already forming vigorously only a few 100 million years after the first stars ignited, it suggests the chain reaction of structure formation was extraordinarily efficient. Stars formed. Those stars enriched gas. That gas cooled faster. New stars formed even more rapidly. Galaxies assembled, all within a cosmic blink. And that leads to a deeper tension with our expectations. Because according to many simulations, the earliest galaxies should be fragile, small, chaotic, their gravitational wells shallow, their stellar populations young and unstable. Yet some of Webb's observations hint at galaxies that already appear structured. Not massive like modern galaxies, but organized, bright central regions, consistent star formation patterns, chemical signatures, suggesting multiple generations of stars, which raises a quiet but uncomfortable question. Were galaxies simply forming earlier than we predicted, or did the conditions of the early universe allow them to grow faster than our models assumed? The deeper astronomers looked, the stranger the timeline began to feel, because once Webb started collecting spectra from some of these galaxies, it revealed something subtle but important. Their light was not purely dominated by extremely young stars. In several cases, the spectral energy distributions suggested stellar populations that had already been evolving for tens of millions of years before the moment we are observing them. That may not sound dramatic, but remember where we are in time. When we observe a galaxy 300 million years after the Big Bang, the universe itself is only 300 million years old. If that galaxy already contains stars that have been aging for 100 million years, then the first star formation inside that system must have started extremely early, possibly within the first 150 to 200 million years of cosmic history. In the language of cosmology, that is very close to the beginning. To visualize it, imagine the entire age of the universe compressed into a single 4-hour day. Midnight is the Big Bang. The first galaxies should begin appearing slowly after the first hour. But Webb seems to be seeing city lights turning on just minutes after midnight. Something is accelerating the process. One possibility is that the first dark matter halos were more efficient at collapsing than expected. Computer simulations often assume dark matter behaves in a perfectly predictable way, particles interacting only through gravity. But if dark matter possesses even slight additional interactions with itself, it could clump faster in the early universe. Faster clumping means deeper gravitational wells. Deeper wells pull gas inward more quickly. Gas collapsing faster leads to faster star formation, and faster star formation leads to galaxies appearing earlier. Another possibility involves the cooling of primordial gas. In modern galaxies, heavy elements help gas clouds lose heat, allowing them to collapse into stars efficiently. But the early universe lacked those elements. Hydrogen molecules had to carry most of the cooling process, and hydrogen cooling is less efficient. Unless something else helped, some researchers propose that turbulence within early dark matter halos could have accelerated gas collapse. Others suggest early radiation backgrounds, or shock waves from the first supernovae, may have triggered rapid star formation across large regions. These mechanisms would effectively shorten the timeline of galaxy growth. Instead of waiting hundreds of millions of years for structures to mature, the universe may have been able to produce luminous galaxies within a much smaller window of time. But there is another explanation that scientists consider carefully whenever anomalies appear in deep-field astronomy: observational bias. Webb is extraordinarily powerful, but even it cannot see everything. The galaxies we detect first are naturally the brightest ones, the extreme outliers that stand above the cosmic background. If early galaxies follow a wide distribution of brightness and mass, Webb's earliest discoveries may simply represent the most luminous examples rather than the typical population. In other words, we might be seeing the cosmic equivalent of skyscrapers before we see the suburbs. Future surveys may reveal that most early galaxies are still small and faint, while a few rare systems grew unusually fast due to favorable conditions. That possibility is one reason astronomers remain cautious when interpreting the earliest Webb data. But even with caution, something interesting is emerging. The early universe appears more productive than expected. Stars ignited quickly, galaxies assembled rapidly, black holes began growing almost immediately, and black holes introduce another layer of tension entirely, because alongside these early galaxies, Webb and other observatories have been finding evidence for supermassive black holes that formed astonishingly early in cosmic history. And those objects may be even harder to explain. Black holes usually begin with death. A massive star exhausts its nuclear fuel, gravity wins the internal struggle, and the star collapses inward. If the remaining core is heavy enough, it compresses beyond the point where any known force can resist gravity. Space curves inward so sharply that an event horizon forms. A black hole is born. That process takes time. First, a star must form. Then, it must live out its life cycle. Then it must collapse. Even the most massive stars take several million years to reach that final moment. Afterward, the black hole left behind begins slowly growing by pulling in surrounding gas and merging with other black holes. This growth is gradual. If a stellar black hole begins with 10 times the mass of our Sun, reaching millions or billions of solar masses requires enormous amounts of time and material. The process is limited by something called the Eddington limit, which describes the balance between gravity pulling gas inward and radiation pushing it away as matter falls toward the black hole. Simply put, a black hole cannot feed infinitely fast. That limit creates a timeline. According to standard models, building a supermassive black hole with billions of solar masses should take hundreds of millions, sometimes billions of years. Yet astronomers have been detecting quasars, extremely luminous objects, powered by supermassive black holes at redshifts above 7. That means these black holes already existed less than 800 million years after the Big Bang. Some of them contain over 1 billion solar masses, and that creates a mathematical tension similar to the one Webb is revealing with early galaxies. Because to grow that massive so quickly, black holes must either start unusually large or feed far more efficiently than typical models allow. Scientists have proposed several explanations. One idea suggests the first black holes formed not from stars but from direct collapse. In this scenario, enormous gas clouds collapse straight into black holes without forming stars first. Instead of starting with a 1-0 solar mass seed, the black hole could begin with 100,000 solar masses or more. That shortcut dramatically accelerates growth. Another possibility involves the existence of primordial black holes objects, formed directly from density fluctuations in the very early universe. If some regions collapsed under extreme gravity shortly after the Big Bang, black holes could have appeared long before the first stars ignited. Those primordial seeds might then grow into the supermassive giants we observe later. Both ideas are still being tested, but they illustrate a broader pattern emerging from Webb's discoveries. The early universe may have been better at building massive things quickly than we previously believed. Galaxies assembling sooner, black holes growing faster, structures appearing earlier. None of these observations alone overturn the standard cosmological model, but taken together, they suggest that the first billion years of cosmic history were more dynamic and efficient than many simulations predicted. And this realization brings scientists to a deeper question. Because galaxies, stars, and black holes all share a common origin, they grew from the initial conditions of the universe itself. If structures formed faster than expected, it may mean those initial conditions were slightly different from what our current models assume. Which brings us back to the beginning, back to the first moments after the Big Bang, when the universe expanded faster than light, when quantum fluctuations became the seeds of galaxies, and when the structure of everything that followed was written into the fabric of space. In the first fraction of a second after the Big Bang, the universe experienced an event so extreme that it still shapes everything we observe today. Cosmologists call it inflation. Inflation describes a moment when space itself expanded at a staggering rate, far faster than anything we see in the universe today. In less than a trillionth of a second, the universe ballooned from a subatomic scale to something astronomically large. That sudden expansion smoothed the cosmos, stretching tiny quantum fluctuations into the density variations that later became galaxies and clusters. Those fluctuations were incredibly small. If you could map the density of matter across the early universe, the differences would be almost imperceptible, roughly 1 part in 100,000. Yet gravity is patient. Over billions of years, those slight variations amplified, pulling matter together and creating the cosmic web. The cosmic microwave background, observed in exquisite detail by satellites such as WMAP and Planck, shows those ancient fluctuations frozen into radiation, released when the universe was only 380,000 years old. Those measurements have become one of the strongest pieces of evidence supporting the inflationary model. They also set boundaries, because if the density fluctuations were too strong, matter would have collapsed too quickly, producing enormous structures long before galaxies had time to form. If the fluctuations were too weak, gravity would never have gathered matter efficiently enough to create galaxies at all. The early universe had to strike a delicate balance, and for decades, the measurements appeared to confirm that balance almost perfectly, which is why Webb's discoveries are intriguing. If galaxies are forming earlier than expected, it raises the possibility that certain regions of the early universe contain stronger density peaks than average. These rare peaks might have acted as gravitational shortcuts, allowing matter to collapse quickly and create galaxies long before typical regions of space caught up. In cosmology, such rare events are not impossible. The statistical distribution of density fluctuations allows for occasional extremes. A region with a fluctuation slightly larger than average could grow much faster under gravity, creating an unusually massive structure early in cosmic history. These regions are sometimes called high sigma peaks in the density field. Imagine the early universe as a vast landscape of hills and valleys, each representing tiny variations in matter density. Most hills are small, but occasionally one rises higher than the rest. Gravity pulls matter toward those peaks more efficiently, turning them into the birthplaces of the first galaxies. If Webb happens to be observing several of these rare peaks, the early galaxies we see may not represent the typical universe, but rather its most extreme environments. But even that explanation has limits, because Webb is not just seeing isolated anomalies. Across multiple deep field surveys, astronomers continue finding galaxies earlier than expected. Not hundreds yet, but enough to suggest that early structure formation might be somewhat more efficient across the universe than previously believed. And this possibility pushes scientists toward new simulations. Researchers are now building increasingly detailed computational models of the early universe, adjusting parameters such as dark matter behavior, star formation efficiency, and feedback from early supernovae. By comparing these simulations with Webb's observations, they hope to understand whether the standard model can accommodate the data with modest adjustments. So far, the answer appears to be maybe. Some revised models can reproduce early galaxy formation if star formation in primordial halos was extraordinarily efficient. Others suggest that bursts of intense star formation could temporarily produce galaxies far brighter than their underlying mass would suggest. In other words, the universe might not be breaking the rules. It might simply be using them more aggressively than we expected. But even if that turns out to be the case, Webb's discoveries still transform our understanding of the first billion years. Because for the first time in human history, we are not merely theorizing about that era, we are watching it unfold. When astronomers talk about watching the early universe unfold, they mean something very specific. Light travels at a fixed speed, about 300,000 kilometers every second, fast enough to circle Earth more than 7 times in a single second. But even that speed is not infinite. It takes time for light to cross space, and space is unimaginably vast. The Sun is 8 light minutes away. The nearest star system is over 4 light years away. The center of our galaxy is roughly 26,000 light years away. When we observe those places, we see them not as they are now, but as they were when the light left them. Extend that idea far enough, and a telescope becomes something extraordinary. It becomes a machine that sees the past. When James Webb observes a galaxy 13 billion light years away, it captures photons that began their journey long before Earth formed, long before our Sun ignited, long before the Milky Way looked anything like it does today. Those photons have been traveling across expanding space for nearly the entire lifetime of the universe. And when they finally arrive at Webb's mirrors, they carry information from the earliest chapters of cosmic history. This is called look-back time, and it is the foundation of observational cosmology. Every deeper observation pushes that look-back time further toward the beginning. Hubble could see galaxies when the universe was roughly 1 billion years old. Webb can now see structures emerging when the universe was only a few 100 million years old. That difference may sound small, but in cosmic terms it is enormous, because the first billion years are where the universe transformed from a dark, featureless fog into a landscape filled with stars, galaxies, and black holes. It is where the cosmic web ignited. To understand why that transformation matters, we need to step back and look at the universe on its largest scale. Not galaxy, not clusters, but the architecture of everything. If you could zoom out far enough tens of billions of light years, you would see that galaxies are not scattered randomly through space. They form patterns, long filaments stretching across hundreds of millions of light years, nodes where those filaments intersect, forming enormous galaxy clusters, and vast empty regions between them known as cosmic voids. Together, these structures form the cosmic web. It is the largest pattern known to exist in the universe, and its origin lies in those tiny density fluctuations created during inflation. Over billions of years, gravity amplified those fluctuations. Matter flowed along filaments like water through rivers, gathering in dense intersections where galaxy clusters formed. Our own galaxy lives along one of those filaments. The local group, the Virgo cluster, the Laniakea supercluster, each part of a larger network stretching across unimaginable distances. In this context, galaxies are not isolated islands. They are nodes in a cosmic structure shaped by gravity and time, which is why Webb's early discoveries raise such interesting questions. If galaxies were appearing earlier than expected, then the cosmic web itself must have begun assembling earlier too. Dark matter filaments would have collapsed sooner. Gas would have begun flowing along those structures earlier. The first gravitational intersections where galaxies ignite would have formed rapidly. That means the large-scale architecture of the universe may have started organizing itself sooner than many models predicted. And that has consequences that extend far beyond galaxy formation. Because wherever galaxies form, stars follow. Where stars form, planets eventually emerge. And where planets exist long enough under stable conditions, life becomes possible. Life is not a cosmological requirement. The universe does not appear to need biology in order to function. Stars ignite, galaxies collide, black holes merge, and cosmic expansion continues whether life exists or not. Yet the ingredients that allow life to appear, heavy elements, stable stars, long-lived planetary systems, are the direct consequences of cosmic structure forming in the first place. The earliest stars were massive and short-lived. When they exploded as supernovae, they seeded the universe with carbon, oxygen, silicon, iron, the elements that later become planets, oceans, and eventually living chemistry. Without those first stellar generations, the periodic table would remain incomplete and the universe would be a far simpler place. So when we talk about galaxies forming early, we are also talking about the chemical evolution of the universe accelerating. If stars ignited earlier, heavy elements appeared earlier. If heavy elements appeared earlier, planetary systems could begin forming sooner. And if planetary systems emerged sooner, the timeline for environments capable of supporting life expands further back into cosmic history than we once imagined. This does not mean life existed in the early universe, but it means the conditions that eventually allow life may have begun developing earlier than expected. Astronomers often think about the universe in terms of habitability windows, not just the habitable zone around individual stars, but the broader cosmic timeline when enough heavy elements exist for rocky planets to form, while stars remain stable long enough for biological evolution to unfold. That window likely began several billion years after the Big Bang and continues today. But Webb's discoveries hint that the build-up of complexity, stars, galaxies, elements may have accelerated the opening of that window, which brings us back to one of the oldest unanswered questions in science. The question Enrico Fermi asked over lunch in 1950. If the universe is vast, old, and filled with stars, where is everyone? The Fermi paradox arises from simple numbers. Our galaxy alone contains roughly 100 billion stars. Many of them host planets. Some fraction of those planets exist in habitable zones where liquid water could persist. Given enough time, chemistry can evolve into biology. Given enough time after that, biology might evolve intelligence. The Milky Way has had more than 10 billion years to run this experiment. Yet when we look into the sky, we see no unmistakable evidence of technological civilizations. No signals, no artifacts, no confirmed visitors, just silence. The paradox is not that life must exist elsewhere. It is that the statistics suggest it should, and yet the sky appears empty. Webb's discoveries do not solve the Fermi paradox, but they subtly change the context, because the paradox depends on assumptions about cosmic history. If galaxies formed later, if heavy elements appeared slowly, if planetary systems required billions of years to emerge, then intelligent civilizations might simply be rare or young. But if cosmic structure assembled quickly, if galaxies ignited early, if heavy elements appeared sooner, then the universe may have had even more time to produce complex systems than we previously assumed. That realization does not prove anything about life beyond Earth, but it widens the timeline, and when timelines widen, possibilities expand, which leads us toward the final part of this journey, because the most powerful discoveries in astronomy rarely come from a single telescope. They come from networks of instruments, each seeing the universe in a different way. No single telescope sees the universe completely. Every instrument is sensitive to a different piece of the cosmic puzzle. Visible light telescopes reveal stars. Radio observatories map cold gas and molecular clouds. X-ray instruments expose violent environments around black holes. Infrared telescopes like the James Webb Space Telescope detect ancient light stretched by billions of years of cosmic expansion. To understand the early galaxies Webb has revealed, astronomers must combine all of those perspectives. This is called multi-wavelength astronomy. When Webb identifies a distant galaxy candidate, other observatories quickly join the investigation. The Atacama Large Millimeter, Submillimeter Array studies cold gas and dust, searching for the raw material fueling star formation. The Chandra X-ray Observatory examines the region for high-energy radiation that could signal an actively feeding black hole. Ground-based telescopes, such as the Very Large Telescope, measure precise spectra, identifying chemical elements and motion inside those galaxies. Each wavelength adds a layer of truth. Radio waves tell us where gas is gathering. Infrared reveals where stars are forming. X-rays show where gravity has become so intense that matter is heated to millions of degrees. When these signals overlap, astronomers can reconstruct the physical history of an object billions of light years away, and the early results from these multi-wavelength campaigns are fascinating. Some of Webb's early galaxies appear to contain surprisingly large reservoirs of cold gas, suggesting that star formation may be proceeding at extraordinary rates. Others show hints of energetic activity near their centers, which could indicate the presence of growing black holes even in these very young systems. Neither result breaks physics, but both reinforce the same theme. The early universe may have been a remarkably efficient engine of structure formation. Gas collapsed quickly, stars ignited rapidly, black holes began feeding early, and galaxies assembled faster than expected. To explore that possibility further, astronomers are preparing for the next generation of instruments. Within the next decade, the Nancy Grace Roman Space Telescope will begin surveying enormous regions of the sky in infrared light, searching for thousands of early galaxies instead of dozens. On Earth, the extremely large telescope will gather light with a mirror nearly 40 meters across, powerful enough to analyze the spectra of faint galaxies Webb can only detect. Together, these observatories will test whether Webb's discoveries represent rare cosmic outliers or the beginning of a broader pattern. If the pattern holds, cosmologists will refine their simulations. Dark matter models may be adjusted. Star formation physics may be rewritten for the early universe. The standard cosmological framework will evolve, not collapse, because science rarely discards successful models entirely. It refines them when new evidence arrives. And Webb will keep watching, orbiting nearly 1 million miles from Earth, shielded from sunlight by a vast sunshield. Its golden mirrors collecting photons that began traveling when the universe itself was young. Every observation adds a page to the story. Every spectrum tightens the constraints on how quickly structure formed. Every faint galaxy deepens the question, how did the universe build complexity so soon? And perhaps more importantly, what else is waiting in that early darkness? 600 million years after the Big Bang, the universe was no longer silent. Stars had ignited across scattered regions of space. Small galaxies flickered into existence along the first filaments of the cosmic web. Radiation from those early stars began tearing electrons from hydrogen atoms throughout intergalactic space, gradually transforming the universe from neutral darkness into a glowing ionized medium. This transformation, the epoch of reionization, is one of the most important transitions in cosmic history. Before it, the universe was largely opaque to ultraviolet light. Hydrogen atoms absorbed radiation efficiently, creating a fog that prevented light from traveling far. After reionization progressed, that fog lifted, space became transparent, allowing radiation to move freely across enormous distances. The galaxies that Webb is detecting lie directly inside this transition. They are not simply distant objects. They are participants in a cosmic turning point, helping illuminate how the first generations of stars reshaped the universe around them. And that makes them extraordinarily valuable scientifically, because reionization is not something we can observe directly as an event. Instead, we infer it from clues scattered across cosmic history. Quasar spectra reveal the last pockets of neutral hydrogen disappearing around 1 billion years after the Big Bang. The cosmic microwave background carries subtle imprints of the free electrons produced during reionization. Deep galaxy surveys show increasing populations of star-forming galaxies as we move forward in cosmic time. But until Webb launched, astronomers could only glimpse fragments of the galaxies responsible for that transformation. Now we are seeing them clearly. Not thousands yet, but enough to begin building a picture. These early galaxies appear intensely active. Star formation rates may be dozens of times higher than what we observe in similar mass galaxies today. Their compact structures suggest gravitational environments where gas collapses efficiently and quickly fuels stellar birth. In some ways, these galaxies resemble cosmic fireworks, short bursts of intense star formation lighting up the early universe. That explosive activity may explain part of Webb's surprising brightness measurements. A galaxy undergoing a starburst can appear far more luminous than its underlying mass would normally suggest. If early galaxies commonly experience such bursts, they could shine brightly enough to be detected at extreme distances without requiring enormous stellar populations. This interpretation softens the tension with cosmological models, but it introduces another question. What triggered those starbursts? One possibility involves rapid gas inflow along dark matter filaments. In the early universe, gas reservoirs were abundant and largely uncontaminated by heavy elements. When gravitational collapse began, streams of cold gas may have flowed efficiently into young galaxies, fueling explosive star formation episodes. Another possibility is frequent galaxy mergers. In crowded regions of the early cosmic web, small proto-galaxies could collide repeatedly. Each merger would compress gas, triggering intense star formation and temporarily boosting luminosity. These processes would make the first galaxy's dynamic environments far more chaotic and energetic than the mature spiral galaxies we observe nearby. And yet, despite their violence, these early systems played a constructive role. They built the chemical foundation of the universe. Each generation of stars forged heavier elements in its core. Each supernova explosion scattered those elements into surrounding gas. Over time, the cosmos grew richer in the ingredients required for planets, atmospheres, and eventually biological chemistry. In that sense, the galaxy's Webb seas are not merely distant objects. They are the ancestors of complexity. Complexity in the universe did not appear suddenly. It accumulated. Every star that exploded added new elements to the cosmic environment. Every generation of galaxies recycled that enriched material into new stars, new planetary systems, new chemical possibilities. Over billions of years, the universe slowly transformed from a simple mixture of hydrogen and helium into a place capable of producing oceans, atmospheres, and eventually biology. That transformation is called cosmic chemical evolution, and the galaxy's Webb is observing lie near the very beginning of that process. Their stars are forging the first heavy elements. Their supernovae are scattering carbon, oxygen, silicon, and iron into surrounding space. Those elements will eventually drift into future generations of stars and planets. In a very real sense, when Webb observes these early galaxies, it is watching the universe manufacture the ingredients that make planets like Earth possible. But that raises another subtle implication. If galaxies assembled earlier than expected, the chemical enrichment of the universe also began earlier. That means the first rocky planets may have formed sooner than our previous models suggested. Planet formation requires heavy elements. A star system composed only of hydrogen and helium cannot produce solid worlds. But once the first generations of stars enrich their surroundings, protoplanetary disks begin containing the materials needed to form rocky bodies. Silicates, metals, complex molecules. These materials gradually accumulate into planetesimals, then planets. The process takes time, but not an extraordinary amount. In our own solar system, planets formed within tens of millions of years after the Sun ignited. If the early universe was already producing heavy elements only a few 100 million years after the Big Bang, the first rocky planets could theoretically have appeared within the universe's first billion years. That realization expands the cosmic timeline for planetary environments dramatically, and it is one reason astronomers are increasingly interested in exoplanet atmospheres and planetary formation across cosmic time. Although Webb cannot directly observe planets around galaxies 13 billion light-years away, it can study the chemical composition of galaxies themselves. By analyzing emission lines in galaxy spectra, scientists measure the abundance of elements like oxygen and nitrogen, key indicators of stellar processing. Those measurements allow astronomers to estimate how quickly galaxies enrich their environments. The results so far suggest that chemical evolution in the early universe progressed faster than many models predicted. which again points back to the same conclusion, emerging from multiple directions. The early universe may have been more efficient at building complexity than we previously believed. But this efficiency does not mean the universe was predictable. Quite the opposite. The first billion years were likely chaotic, filled with turbulent gas flows, violent supernova explosions, rapidly growing black holes, and galaxies merging in crowded regions of the cosmic web. Out of that chaos emerged the ordered structures we observe today. Spiral galaxies, stable star systems, planetary orbits lasting billions of years, civilizations capable of building telescopes. And that final step, the emergence of observers, is the quiet thread connecting this entire story. Because when Webb captures ancient photons from the edge of cosmic history, those photons are being received by instruments built by intelligent beings on a small rocky planet, orbiting an ordinary star in a quiet corner of the Milky Way. The universe spent 13.8 billion years assembling the structures that made that moment possible. For most of human history, the night sky looked permanent. Stars seemed fixed. Galaxies were invisible to the naked eye. The universe appeared timeless. Only in the last century did we discover that everything above us is evolving. Galaxies collide and merge. Stars are born and die. Black holes grow. Space itself expands. And perhaps the most profound realization of all is that the universe has a history, a beginning, a long unfolding narrative stretching across nearly 14 billion years. The telescopes we build allow us to read that story chapter by chapter. First came radio telescopes revealing invisible gas clouds, then optical observatories mapping galaxies across the sky, then satellites measuring the cosmic microwave background, showing us the afterglow of the Big Bang itself. Now the James Webb Space Telescope is pushing our vision even further back, allowing humanity to observe the universe when it was only a few 100 million years old. And with that ability comes a subtle shift in perspective. Because every time we look deeper, we discover that the early universe was not simple. It was active, chaotic, creative. Stars ignited quickly, galaxies assembled rapidly. Black holes began growing almost immediately. The cosmos did not spend billions of years slowly preparing itself for structure. In many places, it built structure as soon as gravity allowed it. This does not mean our cosmological models are collapsing. The framework describing cosmic expansion, dark matter, and dark energy remains extraordinarily successful. The standard model of cosmology explains the cosmic microwave background, galaxy clustering, gravitational lensing, and large-scale structure with remarkable precision. But Webb's discoveries remind us that models are maps, not the territory itself. They describe reality with increasing accuracy, but reality always contains surprises. Sometimes those surprises reveal new physics. Sometimes they reveal complexities hidden inside existing laws. Either way, they move understanding forward. And that is precisely what is happening now. Astronomers around the world are running new simulations of early galaxy formation, incorporating Webb's observations into models of star formation efficiency, dark matter halo collapse, and feedback from supernova explosions. Those simulations will gradually determine whether the early galaxies Webb sees are rare extremes or evidence of a broader pattern across the young universe. Future telescopes will help answer that question. The Nancy Grace Roman Space Telescope will map enormous regions of the sky, identifying thousands of early galaxies instead of dozens. The extremely large telescope will capture detailed spectra from faint galaxies Webb can barely detect, revealing their chemical composition and internal motion. Together, these instruments will transform our understanding of the universe's first billion years. But even before those discoveries arrive, one truth has already become clear. The early universe was not empty for long. The early universe did not remain quiet for long. Within a few 100 million years, gravity had already begun sculpting matter into the first recognizable structures. Gas gathered inside dark matter halos. Stars ignited in bursts of nuclear fire, Galaxies began appearing along invisible filaments stretching across the newborn cosmos. When we observe those distant galaxies today, their light has traveled more than 13 billion years to reach us. That light left when the universe was only a few % of its current age, and yet even then, the universe was already busy, already building, already experimenting with the physics that would eventually lead to planets, oceans, and life. This realization changes the way astronomers think about cosmic history. For decades, the early universe was imagined as a slow awakening, a long period of darkness followed by a gradual emergence of stars and galaxies. But Webb's observations suggest something closer to a rapid ignition. Once gravity gained even a small advantage, matter began collapsing quickly. Stars formed, galaxies assembled, black holes appeared, the cosmic web began stretching across space. In other words, the universe did not hesitate. It began building complexity almost immediately, and that idea carries philosophical weight as well as scientific importance, because when we look at the sky, we are not only seeing distant objects, we are seeing the process that eventually produced us. Every atom of carbon in your body was forged in the core of an ancient star. Every oxygen atom you breathe was created in stellar furnaces long before Earth existed. Those elements traveled through space for billions of years, incorporated into new stars, new planetary systems, and eventually into the small blue world we call home. The galaxies Webb is observing are part of that ancestral chain. They represent some of the earliest factories of complexity in the universe. Their stars created the first heavy elements. Their explosions enriched the cosmic environment. Their gravitational fields shaped the architecture of the cosmic web. From those early beginnings, the universe continued evolving for billions of years until galaxies like the Milky Way emerged, until stars like the Sun ignited, until planets formed, until life appeared, and eventually, until intelligent beings began building instruments capable of looking back across cosmic history to witness how it all began. This moment is extraordinary, because for the first time in the history of our species, we are not merely guessing about the universe's origins, we are observing them. Each faint galaxy Webb detects represents a signal sent billions of years ago, now arriving at the detectors of a telescope orbiting far beyond Earth. Those photons left when the universe was young, when the first structures were assembling, when gravity was writing the opening chapters of cosmic architecture. And now, after traveling unimaginable distances through expanding space, those signals reach us. They reach a species that did not exist when the light began its journey, a species that evolved on a small planet around an ordinary star, a species capable of asking questions about the universe that created it. There is something quietly profound about that, because when we look into the deepest reaches of space, we are not just exploring the cosmos, we are exploring our own origin story. The galaxies Webb is discovering are not merely distant lights. They are echoes of the moment when structure first emerged from simplicity, when gravity first began turning matter into complexity, when the universe started becoming the kind of place where observers could eventually exist. And the deeper we look, the clearer that story becomes. 6 billion light years away, 10 billion, 13 billion. The universe keeps revealing older chapters, and somewhere in that ancient darkness, among the first galaxies that ever formed, the light of creation still travels toward us, quietly, patiently, waiting to be understood. The deeper astronomers examine these early galaxies, the more another quiet realization begins to settle in. What Webb is seeing may not simply be galaxies forming early. It may be the moment the universe crossed a threshold, a point where gravity, chemistry, and time aligned in a way that allowed complexity to begin accelerating. For the first few 100 million years, the universe was dominated by simplicity. Hydrogen and helium filled nearly every region of space. The cosmic microwave background still lingered as a faint glow. Matter had begun organizing into the first dark matter halos, but stars had not yet fully illuminated the cosmic web. Then something changed. The first stars ignited, those stars exploded, and the universe began transforming itself. Supernovae from the earliest stellar generations did more than scatter heavy elements. They injected enormous energy into surrounding gas clouds. Shockwaves rippled through intergalactic space. Gas compressed, fragmented, and collapsed into new stars. In some regions, this process may have created feedback loops. A first generation of stars forms. Their explosions enrich the gas. That enriched gas cools faster. Cooling gas collapses more efficiently. More stars ignite. Those stars produce even more heavy elements. The cycle repeats. If such feedback loops occurred inside the earliest dark matter halos, the growth of galaxies could accelerate dramatically. Instead of slow, steady star formation, early galaxies might experience intense bursts that build stellar mass much faster than modern galaxies typically do. This idea is beginning to appear in new cosmological simulations. Researchers are running updated models that incorporate Webb's observations and allow for extreme early star formation efficiency. In some of these models, the first galaxies can grow far more rapidly than previous simulations predicted. Not because physics is broken, but because early conditions allowed gas to collapse unusually efficiently. The early universe was dense. Gas reservoirs were enormous. Dark matter halos were forming everywhere. When gravity gained the upper hand, the environment may have allowed galaxies to ignite like chains of cosmic bonfires, and Webb is watching the smoke from those fires across billions of light years. But there is another layer to this story that scientists are only beginning to explore, because when astronomers analyze the light from these galaxies carefully, they sometimes notice subtle patterns in their spectra, hints of chemical enrichment already underway, elements heavier than helium appearing earlier than expected. That observation suggests that the first generation of stars, the massive population 3 stars, may have lived and died even earlier than we once believed. If those first stars appeared earlier than expected, then the entire timeline of cosmic history shifts slightly backward. Population 3 stars were extraordinary objects. Formed from pristine hydrogen and helium, they may have reached masses hundreds of times larger than our Sun. Such stars burn through their nuclear fuel at astonishing rates, living only a few million years before exploding in violent supernovae. Those explosions were the universe's first factories of heavy elements: carbon, oxygen, silicon, iron. Before those stars existed, the universe simply did not contain the ingredients needed to build rocky planets or complex chemistry. After they died, the cosmos began to change permanently. Each explosion enriched surrounding gas clouds, seeding them with heavier elements that allowed new generations of stars to form more efficiently. Over time, galaxies became chemically richer, and the universe gradually evolved into the complex environment we inhabit today. If Webb's early galaxies already contain traces of these heavier elements, it suggests that stellar evolution had already begun cycling material through multiple generations of stars very early in cosmic history. That implies something remarkable. The first stars may have ignited within the first 150 million years after the Big Bang. In cosmic terms, that is almost immediately. To understand how extraordinary that is, imagine compressing the entire 13.8 billion year history of the universe into a single calendar year. The Big Bang occurs at midnight on January 1st. The first galaxies Webb is observing would appear during the first week of January. Earth does not form until September. Human civilization arrives in the final seconds of December 31st. In that timeline, Webb is showing us events unfolding during the opening moments of cosmic history. Moments when gravity first began sculpting matter into the structures that would eventually become galaxies, stars, planets, and life. And yet, even as we uncover these early chapters, the universe continues to keep part of its story hidden, because there is a fundamental boundary to how far we can see. Astronomers call it the observable universe. Light travels at a finite speed, and the universe has existed for a finite amount of time. That means there is a limit beyond which light has simply not had enough time to reach us. Anything farther away lies beyond our observational horizon. Even the most powerful telescope ever built cannot cross that boundary. The James Webb Space Telescope pushes our vision closer to that edge than any instrument before it, but it does not eliminate the limit entirely. Some of the earliest events in cosmic history may remain permanently hidden. The birth of the first stars, the exact moment the cosmic web ignited, the earliest collapse of dark matter halos, those events may have happened just beyond the reach of the light that has arrived so far. Yet even with those limits, each observation Webb makes brings us closer to understanding the universe's opening act. Every faint galaxy adds a data point. Every spectrum reveals a new clue. Every deep field survey pushes the frontier of cosmic archaeology further back in time. And what those observations are beginning to reveal is both simple and profound. The early universe was not quiet. It was alive with activity. Stars forming, galaxies assembling, black holes growing, structure emerging from chaos. Structure is the quiet word cosmologists use for everything that exists above the scale of individual stars. Galaxies are structure. Clusters of galaxies are structure. The enormous filaments stretching hundreds of millions of light years across space are structure. Even the vast, empty voids between those filaments are part of that architecture. When we map the universe on its largest scales, what emerges is not randomness, but pattern. Galaxies trace out an immense network, often called the cosmic web. Along its strands, matter flows slowly under the influence of gravity, gathering into dense knots where clusters form and leaving enormous empty regions between them. This architecture took billions of years to emerge fully, but Webb's observations suggest its earliest foundations may have appeared surprisingly quickly. The first dark matter halos formed, gas flowed into them, stars ignited, galaxies began appearing along the first threads of that web, and from that moment onward, the universe entered a new phase of evolution. Because once galaxies exist, they begin interacting. Gravity pulls them together. They merge. They exchange gas. They trigger new waves of star formation. Over time, small galaxies combine into larger systems. Clusters assemble. Filaments grow thicker as matter continues flowing inward. The cosmic web becomes more pronounced with each passing billion years. Our own galaxy is part of that story. The Milky Way formed through a long history of mergers and accretion. Smaller galaxies were absorbed. Streams of stars still orbit our galaxy today, remnants of ancient collisions that happened billions of years ago. Every large galaxy in the universe carries scars from that process, and it all traces back to the moment when the first galaxies ignited. The galaxy's web is observing represent those beginnings. They are small compared with modern giants like the Milky Way. Their stars are younger, their shapes often irregular and turbulent, yet they mark the moment when gravity first succeeded in building lasting cosmic structures. In those early systems, the processes that shape the universe today were already underway. Star formation, supernova explosions, black hole growth, chemical enrichment, galaxy mergers, everything that followed in cosmic history emerged from those first structures, which is why the discoveries Webb is making feel so significant. For the first time, we are not just inferring what those early galaxies were like. We are seeing them. Their faint light has traveled for more than 13 billion years, crossing expanding space until it reaches the detectors of a telescope orbiting far beyond Earth. Those photons left when the universe was young, when the first cosmic structures were assembling, when gravity was transforming simplicity into complexity. And now, billions of years later, that ancient light arrives at a small observatory built by a species that did not exist when the journey began. A species that evolved on a quiet planet, orbiting an ordinary star in the outskirts of a spiral galaxy. A species that learned to ask questions about the universe that created it. And perhaps that is the most extraordinary part of this entire story. Because when we look through the eyes of Webb, we are not only exploring distant galaxies, we are exploring our own cosmic ancestry. Every atom in our bodies, was forged in stars that lived and died long after those first galaxies appeared. The chemical elements that make up oceans, mountains, and life itself are the products of billions of years of stellar evolution that began with the structures Webb is now revealing. The early universe was the opening chapter of a story that eventually led to observers capable of reading it. And as Webb continues to watch the deepest regions of space, more chapters will emerge. New galaxies, new mysteries, new clues about how the universe transformed from a hot, simple beginning into the vast, structured cosmos we see today. Somewhere in that ancient darkness, the earliest galaxies still shine. Their light continues traveling across space, carrying information from the first moments when gravity began building the universe we now inhabit. And every time that light reaches our instruments, it reminds us of something both humbling and profound. The universe has been telling its story for billions of years. We have only just begun to listen.